and you've got a main vein running between those two heads. And so blood squirts from your foot through this muscle up towards the heart. If you're using this muscle, right, that skeletal muscle, when it contracts, it gets shorter and it gets wider. And so when these two parts get wider, they squash the vein that's in between them. And when it squashes them, that blood that used to take up a larger space gets accelerated or pushed back up towards the heart. It helps to push that blood to the heart. You get this surge of blood, right? So if you start using those muscles, that's going to help pump blood back to your heart. Yes?
What keeps you from it separating so that part of it goes backwards in a sense?
We're going to talk about that a little bit later, hopefully today, but it's these valves. So we'll come back to those valves. Right? So there are valves in there that prevent backflow. Right? Yeah, because you would think otherwise when you squish in the middle, half of it goes this way and half goes that way. The valves keep it from continuing to go backwards. Okay? So when are these muscles going to be contracting? Well, when you're active. When do you want to increase venous return? Right? To get the Starling's law of the heart effect. Well, when you're active. So if you're running around using your legs, those muscles are squashing these veins, and that helps to push blood back. Remember, the veins work under very low pressures. And if they're coming from your feet, that's a lot of work to go against gravity. But now these skeletal muscles are helping out the heart, really, by helping to get more blood back to your heart. Okay. So if you're standing for a while and you don't use these muscles, you're not helping that blood come back to your heart. Blood can actually start to pool. You have more and more volume down your legs, less volume coming back up to your heart and available to your head. And so if you get a drop in blood pressure to your head, what happens? You start to see weird colors, or things start to get dark, and then your hearing kind of goes weird, and you get real spacey. You're not about to pass out, right? And you go over, right? One way to help avoid that is don't stand that long, or while you're standing, move around, right? Like when I'm up here, I do not want to pass out when I'm standing in front of you guys, because I don't know what you're going to do to me when I'm out, right? It's either like, get the magic markers out, or run out of the door, right? I shouldn't have given you guys any ideas. So, I'm constantly moving back and forth. Part of it's to go from here to there, but it's also to keep that blood going. So you keep using your legs. When you're up in front of a group, don't just sit there with your legs locked. You're not a horse. You can't do that as well as a horse can. Horses have adaptations that you don't have, right? That allow them to sleep standing up. So you don't want to do that. So a great time to practice this is at the very end of the semester when you guys give your presentations to your lab group. You're going to be standing up in front of everyone for 15 minutes, talking, doing your thing, and you're only going to be doing it for part of the time, and the rest of the time you're standing there waiting for your buddy to finish. Right? While you're waiting, you don't want to just sit there and have your legs locked. It happened once. It didn't end well. So it was late one night in the physiology lab. Presentations were being given. And, you know, they're doing their thing, the group, and then there was this one student that was sort of standing off the side, like right where the little podium thing is in the front of the lab. And this person's waiting, I don't know if she already did her part of the talk or not. She's sitting there, and all of a sudden she starts to go like this. Like, whoa, and boom, she went down. Right? And she made it all the way to the ground, but unfortunately she got the corner of that podium on the way down and busted her head on it. I don't want to have to deal with that again, and I don't want you guys to go through that. It's not comfortable. She didn't really feel it when it happened, but when she woke up, it's like, what the heck? So bad news. So don't sit there and lock your knees. So if you need to, you can go like this the whole time. I don't care. But don't pass out. Right? All right. Questions about how the skeletal muscle pump works? No. All right.
I have a question.
Yeah.
So if that was the calf muscle, when those valves close, it kind of just like, it helps its way along. It's like just like passing it up, basically, through the muscle.
Yeah, you want to get it to the next section past the next
and then
valve.
the valve closes and it goes to the next muscle group.
Essentially, so these valves, they close, they're all operating based on pressure gradients, just like the valves in your heart, passive one-way valves. And when that muscle contracts, the blood's not going to go back this way towards your foot. It gets passed through that valve. And so when the muscles relax, that blood doesn't come back down. It gets caught by that next valve. And then when they contract again, the blood that filled in here pushes through, pushing that blood on, and it just keeps working its way. It's not that it stops, but it slows down. Okay, anything else? All right, so we talked about vein compression. Another contributor, thoracic pressure changes. This would be involving the respiratory pump. So just breathing can help bring blood back to your heart. All right, how does this work? Well, let's imagine our body's laying horizontally so we can sort of remove the effect of gravity, right? Because gravity is going to make it even harder to get blood back to your heart, for instance. So you're laying down and you have atmospheric pressure all around you, squeezing your body, which is okay because your body's mostly made up of fluid that's under biologically relevant conditions, incompressible, at least on the surface of the earth. And so it's pushing it around all over, except you get changes in the pressure around your heart in your thoracic cavity. Right? It's not that you're changing atmospheric pressure, but you're changing the pressure in your thoracic cavity. We haven't really gone over this yet. If we ever get through the cardiovascular system, we'll get to talk about breathing. And we'll see that when you inhale, what you're really doing is decreasing the pressure in your thoracic cavity. Well, what's in the middle of your thoracic cavity? Your heart. So if you got this muscle in the middle and you drop the pressure around your heart, if there's less pressure there, you can take advantage of it. Remember, what drives blood flow from one part of a vessel to the other is a pressure gradient. It goes from higher pressure to lower pressure. To increase the flow, you just need to increase that pressure gradient. You can do it two ways. You can either increase the pressure in these veins out here, or you could decrease the pressure at the heart. So this respiratory pump is decreasing the pressure at the heart. Right? So you drop that pressure there, it increases the pressure gradient, makes it a little bit easier to get that blood back to the heart. So the more you breathe, the deeper you breathe, the easier it is to get that blood back. So when you're just having your normal tidal volumes, right, you're not getting a huge effect with this, but that's okay because you're not very active and you don't need all that increased flow. But if you want an increase in venous return, you're going to be active, which means you're probably breathing harder, right? You start breathing harder and deeper, that's going to drop that pressure around your heart, and that's going to assist in getting blood back to your heart. Everybody see how that works? Good. What else do we have on our list? There's also sympathetic innervation. You can stimulate your veins. This can lead to venous constriction. So you've got all these veins in your body, right? They're at some diameter, and there's some volume of blood in those veins at any one instant. If you stimulate the muscles in the walls of those veins, then those veins constrict. They get smaller. Now there's less volume in those veins. While that extra blood had to go somewhere, it's not going to flow backwards. It flows towards the heart. You just increased venous return. So we've got a few ways now to increase venous return. Questions about that? No. All right, so cardiac output control, we talked about heart rate with parasympathetic and sympathetic innervation, and stroke volume through contraction force, venous return, right? And we broke those down to see what contributes to those, right? And they're actually tied together. You increase heart rate or stroke volume, cardiac output goes up. You decrease one of those, cardiac output goes down. Questions about cardiac output? You guys got it? No, go on.
What was the example for sympathetic innervation? I just got to read it.
So when you have sort of general sympathetic innervation, you have neurons that will innervate on your veins. And those neurons will stimulate the muscles in the walls to constrict or contract that leads to venous constriction. Anything else for that? Okay, so this again represents your whole cardiovascular system for I don't know how long now, we've been talking about just the center portion, right? The pump in the middle of the heart. Now, let's go ahead and take a look at these blood vessels and the blood inside. Okay. Questions about the heart in general before we change over to the next part? No. Yeah.
Specific. But in terms of the, what am I saying? The pressure, like atmospheric pressure and stuff on humans, is that kind of like the effect of what happens when you get like elevation sickness or something? And like the higher you get in elevation, the less pressure there is. There's not, you don't get as much like blood flow or oxygen.
So there's a few other things going on with that. So with elevation sickness, you go higher up in elevation, there is less atmospheric pressure pushing on you, and that can lead to fluid actually filling in part of your lungs, right? So that could be pulmonary edema, right? You can also get cerebral edema, so fluid can sort of accumulate around your brain, and that's all due to a dramatic drop in atmospheric pressure. But also when you go up in elevation, there's less available oxygen. And so that's another complication to it. And so that can lead to problems, and often it's drier, and so you get dehydrated, and you're probably tired, and it's just this big snowball, and can cause some big problems. Okay. Is there another hand that went up? No. Okay, let's talk about blood vessels. We have talked about them a little bit already, but let's just go back to it again. So remember the blood vessels, they connect the heart to all the rest of the tissues of your body. Right? The heart is just the pump, the main pump that's driving this blood flow. And we saw there are other sort of tricks the body has to help the heart out, but the heart is really the main pump. All right. One way we can sort of visualize this is, right, this represents our whole cardiovascular system. It looks kind of strange the way it's laid out. We don't really think of it all as one big loop, but it emphasizes really the two halves of the heart and shows all these different major blood vessels. So the left half of the heart is up top here, and in the drawing it's physically separated from the right half. Again, of course, they're stuck right next to each other in our bodies, but functionally they're two separate pumps. So we've got the left half of the heart that's going to pump blood out into the systemic circulation. The right half of the heart pumps blood through the pulmonary circulation. Okay? So we're going to concentrate on all these different blood vessels here. So let's go ahead and take a look at the vessel types. We've already talked a bit about this. We talked about arteries versus capillaries and veins. We're going to add a little bit more to it now. Right? And this is going to be in order as blood leaves the heart. When it leaves the heart, it enters into arteries. So arteries. These have large diameters. These blood vessels are large in diameter, and they have thick walls. So think about your biggest artery, your aorta. That's receiving all the blood that squirts out of your left ventricle. That's got to be a big blood vessel. And it's under really high pressures. And so you want that to have a nice thick wall so you don't get a tear in the wall as easily. That would be bad news if you did. The arteries lead to smaller vessels called arterioles. And so they're essentially really small arteries. Structurally, they're a little bit different, but they're functionally like little arteries. Blood flows from arterioles into capillaries. Capillaries are going to be very small in diameter and extremely thin. Small in diameter and thin. Remember also that this is where all the exchange occurs in the cardiovascular system. So when we're gaining things in our blood and we're dropping stuff off, that all happens at the capillaries. So if we're going to have all that exchange, you're going to want those vessels to be really thin so it's easier for material to go back and forth. And with the small diameter, you can get lots of them in a given area. All right, once blood flows through the capillaries, it converges into venules. So at this point, we're coming back to the heart. Venules are essentially small veins. So those venules will converge into actual veins. And veins are also large in diameter and thick-walled compared to capillaries. Okay, everybody have that? All right. Let's look at the walls of our blood vessels. Okay, so we can sort of break it down into a few different layers, and then we'll compare the different vessel types to see how they vary. All right, so there's an epithelium. This is what's going to line the inside of our blood vessels, and it acts for most of our blood vessels as a barrier. So it keeps whatever's in the blood, and it keeps whatever's outside from getting in there. Epithelium. So for most all your blood vessels, that's what lines those vessels. Then as you work your way out through the wall of the blood vessels, there's elastic tissue. Right? So if you stretch the wall of a blood vessel, it'll snap back to its original size. And this will be important in recoil, so we'll see that later on. Right, so if it swells up, it'll recoil back to its smaller size. Also in the walls of our blood vessels, we will find smooth muscle. And when that muscle gets stimulated, it leads to constriction. So then the blood vessel would get skinnier. And then outside the elastic and muscle tissue, we would find a fibrous tissue, which is thick and durable, and that protects the blood vessel. So it makes it harder to puncture a wall through the, or a hole through the wall of the vessel. All right, let's go ahead and look at a diagram that kind of puts all this together. Everybody ready? Okay. So what do we have here? On the left side we have veins and venules. On the right side we have arteries and arterioles. And in the middle is representing capillaries, purple here. All right, so we've got that fibrous layer on the outside, the thick, tough portion on the outside. There's smooth muscle and elastic tissue, so the blue Swiss cheese is supposed to be elastic tissue. And then we've got that endothelium lining the inside, acting as a barrier. And we can see that in arteries, we can also see it in veins. When you start looking at some of these skinnier vessels, we don't see all those parts. Let's go all the way down to the capillaries. So the capillaries are the simplest of the blood vessels. They don't have all that stuff in the walls. All they have is that inner layer. Right, that epithelium. It's a single layer of cells. They don't have the elastic portion or the muscle portion or that fibrous part on the outside. It's just a single layer of epithelial tissue in there. So it's really easy for chemicals to go back and forth. And you can see these are very thin walls in the capillaries compared to the arteries. Right? The arteries have really thick walls. And the arteries have much bigger diameters than the capillaries. This isn't necessarily drawn to scale. We can also see that with the veins. The veins have all those parts. They're much bigger and thicker than the capillaries. This figure shows basically the same thing, but it sort of breaks down some of these parts a little bit better. See the capillaries are very, very thin with one cell layer, where the veins and the arteries are much thicker. But also notice, if you compare the arteries to the veins, arteries are going to, for a given diameter, have a thicker wall than the veins. And why is that important? Now, you're going to have a higher pressure in the arteries. So you need more protection. You need it to be a thicker, tougher blood vessel. Right? So arteries are going to have thicker walls than veins are. Also, veins are going to have valves. Right? So we mentioned valves earlier when we talked about the skeletal muscle pump. You've got valves in those veins, but you don't have them in the arteries. Why don't you need them in arteries? Because what? Well, the blood's only going in one direction in the veins also. It's the same reason the arteries are thicker, right? It's the pressure. Much higher pressures we're working with in the arteries. So you don't really run the risk of blood flowing backwards in the arteries because of the higher sustained pressures. It only becomes a potential problem in our veins where the pressure is much lower. So those veins have valves in them to prevent backflow. Okay? How does everybody feel about different types of blood vessels, comparing them all? Feel good? Questions? All right. Let's talk about blood pressure. Right, blood pressure is important. This is what drives blood flow. Without pressure, you're not getting any flow. So let's make sure we get a good handle on the blood pressure. All right. What initiates the blood pressure? What's the source and the origin of all the pressure we get in the cardiovascular system? It's really coming from those ventricles. That's what charges up the cardiovascular system each cardiac cycle. When you squeeze down on the ventricles, and then during ventricular ejection, all that blood squirts out into those arteries. Those arteries swell up, they get all that pressure in there. That's where we sort of get charged with the pressure, uses that pressure through the rest of the cycle. So what sustains the pressure? Because remember, with those ventricles, when they squeeze down, they generate those huge pressures. That's where it all comes from. But the ventricles don't keep that high pressure. If they're going to get filled up again, they need to have really, really low pressures. So ventricles have to have the highest pressure in the cardiac cycle. They also have to have the lowest pressures in the cardiac cycle so they can fill up again. But when that pressure drops in the ventricles, we don't get a stop of blood flow. Blood continues to flow through our blood vessels throughout the cardiac cycle. So what is going to sustain that pressure? If we don't have pressure in the arteries, right, then blood flow is going to stop. So those arteries need to somehow sustain that pressure. Keep the pressure high throughout the cardiac cycle. Okay, let's look at a drawing. All right, so let's imagine here on the left, this represents the ventricles. We've got, or we can even just focus on the left ventricle. Let's say this is the aorta. During ventricular systole, the ventricles contracts down, squirts blood through the semilunar valves, which you can see here is open, into, in this case, the aorta. When the ventricle squirts all that blood into the aorta, that blood does not shoot straight through the aorta. Most of that blood stays in the aorta for a moment. And what happens is the walls of the aorta swell up, they stretch out to hold that volume of blood that just squirted in there. If the ventricles contracted and all that volume of blood went straight through the aorta, then when the ventricles relaxed, there wouldn't be any pressure or blood to keep flowing through the blood vessels. So, ventricles contract down, blood goes into the aorta swells and stretches up. And that's what we see here. Once the ventricles relax, the semilunar valves shut, now the elastic tissue in the walls of the aorta are going to recoil slowly through the rest of the cardiac cycle. And as they do that, they're going to continue to push blood through the through the blood vessels. So, when the ventricles contract, you're going to load up pressure in the walls of the aorta, and it slowly releases that pressure through the rest of the cardiac cycle. Right? So that's what helps sustain that pressure. This also leads to a pulsatile circulation. So even though blood continues to flow throughout the cardiac cycle, flow through our blood vessels, the pressure is not constant in our arteries. It fluctuates. Right when we get that surge of blood from the ventricles, the pressure shoots up in the arteries. And then as the ventricles are relaxing and filling up again, that pressure slowly drops. Right? As we release the pressure from the aorta, that total pressure starts to go down, down, down. And then eventually the ventricles contract again and the pressure shoots up. And then the pressure goes down, down, down. It never gets that low, it stays pretty high, but it fluctuates up and down. And that really is this pulsatile circulation. It's an alternating systolic and diastolic pressure. Okay? We got that, Deb? All right, we've seen this figure before. And let's concentrate on the left side. It's a little more exaggerated. You can see that the pressure in the ventricle, this is, right, so as we go along the horizontal axis, this actually goes through the different blood vessels, starting at the arteries, receiving blood from the ventricles, going all the way through arterioles, capillaries, venules, veins, back to the heart. And we have pressure in these different vessels on the vertical axis. So right before the beginning of the graph would represent really the ventricles. All right, so the pressure in the aorta, for instance, right outside the left ventricle, is going to fluctuate up and down. And that's reflecting the ventricles contracting and then relaxing. When they contract and spurt blood into the aorta, that aorta stretches, gets loaded up with pressure, the pressure shoots up. And that highest pressure we call the systolic pressure. And then the ventricles are relaxing. Semilunar valves are shut and the ventricles are filling up. The aorta slowly recoils, releasing that pressure. So that pressure drops back down. And then at this low point, this is the diastolic pressure. And at that time, when the pressure starts to go back up again, that's due to the semilunar valves opening, blood squirting back into the aorta from the ventricle, the left ventricle. So it goes up and then back down. And this swing in pressure, right, or this pulsatile pressure, we can see travels through the blood vessels. Right? Think of it as waves of pressure pushing through the blood vessels. And so you can pick them up in your arterioles. Right? But by the time you get out to the capillaries, these swings have dampened dramatically. And they're essentially gone in the capillaries, and then when you're in the venules and veins, there's no fluctuation in the pressure. So the walls of the blood vessels start to absorb these swings in pressure, and it gets dampened as you go farther from the heart. So where do you get the big swings? Right outside the heart, in our main arteries. Right? So where do we usually measure blood pressure? With the brachial artery, so that's right at your arm, which is a quick branch off of your aorta. It's about as close as you can get to your aorta without being really invasive. Right? You don't want to sort of crack your chest open to go stick something around your aorta. Okay? So that's what these swings are coming from, and that's your pulse, right? Wherever you have arteries that come close to the surface of your skin, you can actually feel these pressure waves, and that's your pulse, right? So you can feel it in your neck, in your carotid artery, radial artery at your wrist, brachial artery, you can feel it. There's a number of different places around your body where you can feel this, and that's your pulse. Keep in mind, though, that that's not your heart rate. Right? You can feel your heart rate by actually feeling your heart thumping in your thoracic cavity, but when you feel your pulse, you're feeling this wave of pressure, which is directly correlated to your heart rate, but it's not measuring your heart rate directly. Can you see the difference there? All right. We got that worked out. Yes?
Are blood clots like most susceptible like in veins because the pressure is so low? Like it's going.
I would imagine that, yeah, in lower pressure system, it's easier to get stuff sort of clogged up because you're not blowing it through. But also skinnier vessels, right? So you can get blocks in your arterioles and capillaries because those are constrictions, right? From an artery to an arteriole, it gets smaller, and capillary gets smallest. And so if you've got some chunk in there, it's most likely to get stuck on the upstream end of the capillary.
And are all of these the same diameter throughout the body? Like, I mean, of course, in their own way, like are all veins pretty much in the same diameter? Or are they very
No.
Okay.
No, not necessarily. So just think about you've got your aorta. That aorta divides into many other arteries that are each smaller than the aorta. Okay, so the further away from the heart you are,
Small.
as you approach the capillaries, the smaller the diameter.
Yeah.
But then when you go from capillaries back to the heart, it gets bigger and bigger in diameter, but fewer in number. Okay? All right. With this change in pressure, so we've got this drop in pressure all the way through, which we need to keep blood flowing. But notice that this pressure down here in the veins is really, really low. There's very little gradient to work with to get blood through these veins and back to the heart. So your veins could use some help. getting blood back to the heart. We've already kind of talked about this, right? So when you're standing for a long time, you want to keep those muscles going, take advantage of the skeletal muscle pump, for instance. So let's go through mechanisms of venous return. I know we just went through it before, but let's do it again just to make sure it's fresh in our head and from a different perspective. Because before we were thinking about venous return increasing, leading to an increase in stroke volume. Now I want you to think about it in terms of, let's just make sure we get venous return. Let's have enough pressure to get blood back to the heart, especially from places like our feet, which is pretty tricky because we have to work against gravity. All right, so as we mentioned, the skeletal muscle pump. This is an important player. So we talked about how main veins can run between muscles or between parts of a muscle so that when those muscles contract, they squash the vein, pushing blood back towards the heart. And it was brought up, what keeps the blood from flowing backwards? Well, we have valves that prevent backflow in our veins. Right? And we also have that skeletal muscle pump that we've been talking about. All right. Got that? All right. So we go back to our drawing here. So again, the vein goes through the muscles contract, squash the vein, push blood back to the heart. The valves keep it from going backwards. So we have these valves in our veins. We don't have them in our arteries. These valves, though, are pretty cool. You can actually, since you've got a lot of veins close to the surface of your skin, you can see these valves working. Right? So let's imagine we've got a vein here, and blood is going to be going through the vein up towards the heart, and you're going to have some valves in here. So when blood flows through, say it makes its way up into here, if the pressure drops and that blood starts to fall backwards, these passive one-way valves will seal, keeping the blood from going backwards. Again, it's just like the valves in our heart. Only in our heart we're dealing with much bigger pressures. So to see this work, what one could do is you could take your finger and let's go ahead and squash a vein. So you squash it so that we're not going to allow more blood to come into the blood vessel in this section. Okay? So blood normally would flow through. We're going to keep more blood from coming in. And then we can take another finger and we can push blood in this vein towards the heart. You don't want to push it backwards or you can blow out your valve. So you push it towards your heart, and if you go past the valve, lift your finger up, this blood will try to flow backwards